The clue did not look like a planet. It looked like a barcode carved into infrared light. Welcome to Cosmic Enigma, where we follow the evidence behind the universe's most surprising discoveries and separate what astronomers know from what they are still testing. In a field washed with starlight and dust, a repeated pattern of carbon monoxide absorption appeared, where astronomers expected a smoother glow. That pattern belonged to an atmosphere. The object producing it was Beta Pictoris d, a giant world hidden inside one of the most intensively studied planetary systems near the Sun. Webb had not been sent to discover this planet. The telescope was examining a world astronomers already knew, Beta Pictoris b. Yet, the near-infrared spectrograph recorded both a small patch of sky and a spectrum at every position. Inside that three-dimensional data cube, chemistry exposed what ordinary brightness had failed to reveal. The discovery began with a warning that matters far beyond this one system. A planet does not always announce itself as a clean dot. Sometimes its molecules speak first. Beta Pictoris is close by astronomical standards, about 63 light-years from Earth and remarkably young, roughly 23 million years old. That youth makes it a living laboratory. Around the star lies a broad disk of debris, dust and fragments continually supplied by collisions among asteroids, comets, and planetesimals. We see the disk nearly edge-on, a bright lane extending across the system. Two giant planets were already known inside it. Beta Pictoris b became famous as an early directly imaged exoplanet, while Beta Pictoris c follows a tighter orbit. But that same brightness and complexity created camouflage. Dust scatters stellar light, builds knots and streaks, and produces structures that can imitate a faint companion. A well-studied system can therefore remain full of blind spots, especially when the missing object is dim and embedded in the very material scientists are trying to understand. Beta Pictoris d occupied one of those blind spots. Independent observations from the European Southern Observatory later showed just how severe the problem was. In ground-based images, the new planet is about 100 times fainter than Beta Pictoris b. It sits near the glare of a brighter neighbor in some epochs, and near luminous disk structure in others. A suspicious bright patch was not enough, because instruments, dust, and imperfect starlight removal can all leave false features. Once astronomers knew the planet's likely path, however, they returned to stored observations and recovered it in images reaching back as far as 11 years. The evidence had been recorded long before the discovery was secure. Archives are not dead collections. New methods, better orbital predictions, and a single unexpected signal can transform old pixels into a time series, allowing a possible object to become a moving member of a planetary system. Webb's decisive advantage was not sharper photography alone. Its near-infrared spectrograph integral field unit divides a small scene into many spatial elements and records a spectrum for each one. Molecules absorb particular wavelengths according to their structure, leaving a recognizable sequence of dips. Carbon monoxide in a giant planet's hot atmosphere produces a dense, repeated pattern. Astronomers can compare the observed pattern with templates and ask where in the field that molecular signature is strongest. Smoothly reflected or scattered, dust light does not produce the same narrow sequence. The planet could therefore be separated, chemically even while it remained visually entangled with the disk. Its broad brightness was difficult to trust, but its atmospheric fingerprint had a structure that dust could not easily counterfeit. The Discovery team describes this as the first planet found through spectral template matching with moderate resolution spectroscopy, a method built to recognize composition rather than merely contrast. Chemistry supplied the candidate, not the final verdict. A carbon monoxide-bearing source might still be unrelated, perhaps a background object projected near the disk, or an artifact that survived data processing. The spectrum provided another measurement, radial velocity, which is motion toward or away from us, inferred from small shifts in the molecular pattern. The team compared that velocity with the source's position and with the orientation of the debris disk. Those pieces agreed with an object, orbiting Beta Pictoris. A background star or brown dwarf would have needed to reproduce the molecular spectrum, appear in the correct place, move at the correct speed, and align with the system by chance. Discovery is not a bright spot followed by a name. It is a chain of tests in which independent properties must converge on one physical explanation. Here, spectrum, speed, geometry, and repeated observation all pointed toward a third giant planet. Follow-up observations strengthened that chain. Webb returned with its mid-infrared instrument and detected water vapor and methane, adding 2 more atmospheric signatures to the carbon monoxide evidence. A second epoch also helped show that the signal persisted and behaved as an orbiting source should. Meanwhile, the separate ground-based team detected Beta Pictoris d with a very large telescope and traced it through older telescope archives. Webb's near-infrared spectroscopy, Webb's later mid-infrared chemistry, modern ground-based imaging, and decades-spanning archival positions did not depend on one identical failure mode. Their agreement made the planetary interpretation far harder to dismiss. One dataset can identify chemistry, another can reveal motion, and an archive can supply the missing years. Together, they turn a serendipitous feature into a confirmed member of a system already known to contain 2 other giant planets. What kind of world is Beta Pictoris d? The first portrait is necessarily provisional. Atmospheric model fits combined with models of how young giant planets cool suggest a mass of roughly 2 to 4 times Jupiter's. That makes it smaller than the system's 2 previously known giants, which are each closer to 10 Jupiter masses. Orbital fits, radial velocity, astrometry, and stability calculations point to a wide path with a semi-major axis around 30 astronomical units or greater. It is the widest of Beta Pictoris, 3 known planetary orbits. Yet it remains inside the debris disk's inner edge. Mass depends on atmospheric and evolutionary models, while the orbit is constrained from only a limited fraction of a very long revolution. More observations can shift both estimates. The location may solve an older puzzle. Beta Pictoris debris disk does not fade inward as a perfectly featureless cloud. It has a sharply defined inner region and other structures that have invited gravitational explanations. A planet with Beta Pictoris ds estimated mass and position can help carve that boundary, scattering, or redirecting smaller bodies over time. The discovery paper finds the wide orbit consistent with such a role, and the independent imaging team reaches a similar conclusion. Dust responds to collisions, radiation pressure, gas, and the combined gravity of several planets. The new world is therefore a compelling missing piece, not a complete solution by itself. Astronomers are no longer inferring an unseen sculptor solely from a disk's shape. They can now test a specific planet's orbit and mass against the structure it may have created, turning a broad hypothesis into a set of measurements that future observations can challenge. Beta Pictoris now joins HR 8799 as only the second known system with more than 2 directly imaged planets. Multi-planet images are rare because host stars overwhelm their companions, and because the easiest worlds to photograph are young, warm, massive, and widely separated. 3 planets in one young environment offer something unusually controlled. Scientists can compare worlds that formed around the same star and within the same disk. Traditional imaging asks whether a point is bright enough and distinct enough to survive the glare. Spectral template matching asks whether a molecular pattern is present, even when the object's overall light is confused with dust. It also suggests that carefully re-examining existing spectral cubes and image archives could expose companions that were recorded, but never isolated. Additional positions across the orbit can tighten the semi-major axis, eccentricity, and relationship to the disk. Better dynamical constraints can test whether the planet truly has enough mass to sculpt the inner edge. Broader and more precise spectra can refine its temperature, clouds, chemistry, and formation history. Beta Pictoris d was hidden because nature placed a faint atmosphere behind a luminous, structured foreground. It was found because spectroscopy converted that atmosphere into a recognizable code, and because astronomers demanded that chemistry agree with motion, geometry, and time. The lesson is beautifully restrained. Even a famous system can hold an unrecognized world, and seeing it may require listening to the structure of its light rather than trusting the brightest shape in an image. If this evidence first investigation changed how you think planets are found, please like the video. Share it with someone who still imagines every new world appears as a bright dot. And subscribe to Cosmic Enigma for more mysteries solved one observation at a time. Before you read anyone else's answer, commit to one in the comments. Which follow-up measurement would most change our understanding of Beta Pictoris d, its mass, its orbit, or its atmosphere, and why.